What does it mean to fall? Why do we fall downward? Is there some center hidden below that pulls us infinitely? This time, we begin with a very simple question. What makes us fall downward? This city, famous for its hectic mornings, seems different today. People on the street have all come to a standstill. What's caused them to pause their daily routine? Something remarkable is unfolding in the sky this morning. In Tokyo, it's the first time in 173 years. Suddenly, daylight turns into darkness. Confronted with this once-in-a-lifetime spectacle, Tokyo's morning is filled with anticipation. The total solar eclipse reaches its maximum at 7:20 a.m. The moment the sun slips behind the moon, the universe offers a glimpse of its hidden secret. One of Einstein's most enthusiastic supporters was also watching this cosmic event. In 1919, the British astronomer Arthur Eddington used a telescope to observe this eclipse. He had just one question: can starlight be bent by gravity? During a solar eclipse, the sun, moon, and earth line up. The sun is masked by the moon, and the sky grows dark. At such times, stars come into view. But stars behind the sun shouldn't normally be visible from Earth. Yet Eddington managed to photograph one of those hidden stars, an observation that forever changed one person's destiny. Albert Einstein was 27 when he put forward his special theory of relativity, yet a year later, his everyday life hadn't improved much. Though he had been promoted to Technical Expert Class 2 at the Patent Office, he was dealing with a son in a challenging age, and a wife, once a fellow physics student, who could no longer keep pace intellectually. The single overriding concern in Einstein's mind was that special relativity offered no way to incorporate gravity. Special relativity is a theory of uniform motion, while gravity requires dealing with accelerated motion, so the two seemed incompatible. What does it really mean to fall? This straightforward question took aim at the revered legacy of Isaac Newton. In London, the Royal Society, dedicated to advancing knowledge of nature, stores a wealth of scientific volumes in its underground archives. Founded in 1660, it holds one book above all: Newton's Principia. Written in Latin across 3 volumes, Newton published it at age 45, but many core ideas originated in his early 20s. One question guided him toward understanding how the universe works. What does it truly mean to fall? Newton returned to his childhood home at age 23, when an outbreak of the plague shuttered his college. Historians call 1665, his year of return, the miraculous year. He spent 2 years in his old family house, immersing himself in math and philosophy. Ample research puzzles awaited him right outside his doorstep. For instance, objects on Earth drop down, so why does that large moon in the sky not fall as well? What force keeps the moon orbiting Earth? These musings confronted a worldview that had reigned for 2,000 years. Aristotle reasoned that earthly and heavenly movements differ because Earth is inherently flawed, while the heavens are wholly perfect. So naturally, their motions must diverge. Celestial bodies, in perfect circular motion, never collide, orbiting around the center. And at that center, he placed the world we inhabit. Meanwhile, the terrestrial realm was constantly changing and thus deemed imperfect, formed by 4 fundamental unchanging elements: fire, air, water, and earth. Each one returned to its natural place by a sort of built-in principle, so stones fell back to the ground because they were meant to be there. Newton didn't subscribe to that explanation. Why should the earthbound apple and the heavenly moon behave so differently? He took his clue from Galileo's law of inertia. It states simply that a body in motion remains in motion, and a body at rest remains at rest unless acted upon. We experience this daily. When your car halts suddenly, you lurch forward. When it accelerates, you're pressed backward. Without an outside interference, something in motion keeps moving, and something at rest remains still. Newton posited that the same law applies equally to the moon, or to a thrown ball. However, a thrown ball follows a parabolic arc and lands, thanks to gravity. But there's a trick. You can stop it from landing by lowering the ground continuously. Eventually, if you keep removing Earth's surface, the ball orbits Earth, never hitting the ground, while constantly falling. That was Newton's vision and the foundation for the idea of artificial satellites. Likewise, the moon circles Earth as if it were a satellite, always falling but never quite hitting. So what about the moon? And the apple makes them both fall. Newton concluded that there must be a mutual pulling force between them. He encapsulated this in a universal law. Although the final equation appears complicated, put simply, two objects pull on each other. The more massive they are, the stronger the pull. The farther they are, the weaker the pull, specifically diminishing by the square of the distance between them. In frictionless space, a walnut and an apple would draw together, even though Newton himself never traveled to space. He found that the downward acceleration of an apple and the moon's orbital path match the same principle. If the distances they fall coincide, that suggests they're under the same force. Newton forwarded his findings to the Royal Society, assembling them into Principia. One can only imagine his excitement in discovering the universe's workings from a rural English hamlet. Everything in the universe follows this law of universal gravitation. Tides, too, are explained by it. But then came a puzzle. If the moon suddenly vanished, we'd need 1.5 seconds to realize it visually, since light takes that long to travel from the moon to Earth. Yet Newton's theory implied that gravitational changes would be felt instantaneously, outrunning even light, which was contradictory. As of 1907, Einstein still wrestled with that conundrum. Overcoming Newton demanded an insight Einstein later called his happiest thought, the realization that gravity and acceleration are identical. Someone in free fall doesn't feel their own weight. In that moment, the domain of gravity simply vanishes. That was Einstein's happiest idea. Because gravity is understood as acceleration, he spent 9 more years perfecting these views, culminating in the general theory of relativity. Falling, he said, emerges from the curvature of space. Even light bends when traveling through this curved geometry. Eddington's observation of starlight curving around the sun during a solar eclipse verified Einstein's predictions. Thus, Newton's era closed, and a new one rose. In 1930, Einstein visited Eddington at the Cambridge Observatory, a historic meeting between a grand theoretical concept and its empirical validation. And so, the seemingly magical tale drew to a close.